changing world. Our role continuously changes. It's like what was a problem 30 years ago, big problem 30 years ago, is no longer a. And what is problem today may not be the problem in 30 years time from now. So we need to really be adaptable, remembering we are there to serve the society. So the subtext is the observed damage and lessons learned from some of the recent earthquakes. And as I said, it falls under the title that we want to try and design these pile foundations to withstand extreme loads and like dynamic loads. And therefore, it is relevant that we look at how some of the damage is. And what do we mean by resilient infrastructure? And we take the definition of resilient infrastructure within as that which can withstand extreme events. For example, earthquakes, tsunamis, volcanic eruptions, flooding. And I'll show some examples of each of these. More importantly, if I want to study these kind of extreme load events, how do I go about doing research? These are extreme events, so they're not going to happen every day for me to instrument a building and see how it performs or do things like that. So we need to have some research strategy. And once you kind of are able to create that, how do engineers then go about creating some infrastructure that is resilient to these extreme events? And then I'll try to summarize, and I'll be happy to answer questions. I've been teaching for the last 35 years now, so at any point if you feel I'm not sure what he's on about, put your hand up and ask me. And that won't throw me off my lecture, and I can always go back and restart where I left. So feel free to do that at any point. Some history, right? 200 years, the Institution of Civil Engineers has been in existence in the UK. And in 2018, we celebrated 200 years. Now it's been another 7 years, so it's 207 years to be up to date. There are few key civil engineers who played a role, who are not actually, never call themselves civil engineers, although they founded the Institution of Civil Engineers. One is Brunel. You may have heard of him. Isambard Brunel is a famous engineer. He built everything from ships to trains. He had invented a different gauge, not the broad gauge, but broader than the broad gauge. I'm going to pick on the bits Brunel has done in terms of tunneling. This is back in the day in 1700s when people didn't know what tunneling was, right? They were very scared. And this man then comes up with and constructs the first tunnel below River Thames. Okay, this is going through London Clay before River Thames, and he started that in 1826 and it got finished in 1847. He had to come up with so many different things, like how do you support the tunnel after it's constructed? How do you support the face from soil falling back into the workers? He has come up with ideas like this, where he would create a box. Each box is big enough to hold a man with a pickaxe, and they would excavate the clay in front of them. And like that, they constructed the tunnel layer by layer going forwards, and all by hand. And they were very worried that the Thames River, which is above, but he made it work. Then the tunnel finished, and nobody was using it because they could see the entrance was on the left bank of the River Thames, and the exit was on the other side. So they knew the thing was through, but they also knew it was going underwater. They thought, oh, this might all leak water at some point, and we'll all get drowned. So nobody was using the tunnel. Then he came up with this idea that he will hold a banquet in the tunnel. You can see the picture here, and invited all the big and mighty in London to come and have a dinner in the tunnel below River Thames. And once that has happened, then people started using it slowly. So he had to not only make the structure, but prove to the society that it is actually safe. Was that there in 2 days ago. How much rainwater is everywhere stored? My guess is not much. So engineering means you got to solve problems, and you must have the foresight to size the things appropriately. Anyhow, this man did the London tunnels. As I said, they're still operational, and the network is quite vast. This is the map of London, where he managed to get the sewer water out of London into Thames using these tunnels. So those were the challenges in 1800, right? So old tunnels for transportation of people, water, and sewage, right? And as a result, London continued to grow, and in fact, it is still continuing to grow today. It's about 20% of UK population lives in and around in what we call Greater London area. That is, 1 in 5 British people lives in London. So the rest of the country, they are only vastly spread out. In Scotland, which has more than uh, maybe 40% of the land area, has a population of something like 6.5 million. So it's really sparsely populated, and it's also very cold up there. Now, our challenges are now changed compared to 1800s. Now we have to do things in the backdrop of, say, climate change, rising water tables, and other risks, some of which I will talk about. So modern civil engineers need to innovate in delivering the solutions that are required today. This infrastructure that we need today is very different from what was needed back in 1800s. So I'm going to pick a couple of examples of more recent projects in London again. So this one is called Crossrail. Crossrail basically was this tunnel is about 8 meters. Okay, it's fairly large tunnel, and two of them, upline and downline, and you needed to worry about the tunnel going below pile foundations of existing buildings, or the tunnel actually crossing other metro lines already there. We already have 3 levels of tunnels for current ones. This one had to go below all the existing 3 lines. So how do you go about it? So they had some shafts at Bond Street and other places. I'm not going to focus too much. And this Pudding Lane portal is the important one. And they had to put shafts here. Forget the name places. I'm going to show you. So first thing, to make a new tunnel, you need to make a vertical shaft that goes into the ground. So this is the plan view, and you're trying to create a circular shaft to drop your tunneling machine in. So the size of the tunneling machine is about this. This is the 8 meters in diameter, and you can see the cutters and process fluids that you need to inject to treat the clay so that it comes out as a flowing liquid, so that you can pump it out. So this whole EPP, the earth pressure balancing machine, is a fairly complicated beast, and it needs to be lowered into the ground. So you take this and then lower it into the shaft, as you can see here, and so they then land at the base, and then they can start tunneling horizontally to create the tunnel itself. And you also line the tunnel as the tunneling machine goes. So there are two machines. One obviously is called Elizabeth, the other one is called Victoria, which started doing this. This is a very old slide from my colleague and former professor, Robert Mayer, and he looked at this tunnel collapse mechanism I think he's done his PhD in 1974 or something like that. And as a result of this one slide, he became very famous, started his own company called GDG, and they are the consultants world over at the moment to, if anybody wants to make a tunnel or have problems with tunnels, they will go to GDG in London, and he owns the company. So this is a very powerful slide. What he has put in his PhD thesis made his career lifelong. And what he was doing is he tried to do centrifuge modeling. I'll come and explain maybe tomorrow what centrifuge modeling is and how we do that. But basically, it's a realistic way to model what happens. And he could create the tunnel and observe how the collapse happens in an experiment and what will be the consequences for the structures on the surface. So this ground collapse is a very big problem, especially when the tunnel goes shallow. Deep tunnels are generally more safer than shallow tunnels. And on the ground, if the tunnel collapse happens, and that is not just an experiment, things like this happen as well. This is in Munich, I think, somewhere. And this kind of sinkholes open up, and a bus was going. Suddenly, this opened, and the thing fell in because they were trying to tunnel underneath, and this whole ground has fallen into the opening that the tunnel created. It's not just limited to the Germans. We have our share of disasters, and this tunnel collapse happened on when the Heathrow line was being built, Heathrow Express line. And the only thing that was funny about this tunnel collapse is the buildings, the porta cabins you see there belong to a company called Balfour Beatty, and their own die is because if you look at the far end, there are traffic lights there, and they were red at the time when the collapse happened. Because they were red, all the traffic was held behind, and so that's another reason why we should not ignore the red lights and go through red lights easily. And luckily, casualties were less. But this went, Singaporeans are very, very strict about health and safety and everything else. So this went up to the highest levels in Singapore government. Robert Mayer, the GDG were consultants on looking at the collapse. He was on the committee and all that kind of stuff. But really, if you don't understand the mechanics of the soil mechanics properly, things like this can happen. Okay, those are the bad things, right? What can we actually do? I'm going to give you an example of a Jubilee line extension. And the Jubilee line extension happened maybe 10, 12 years ago now. And this picture you should recognize. This is the Big Ben. And this is our parliament, British parliament, right? So opposite this, they wanted to create a new, the Jubilee line runs underground below. So this is River Thames, and the line kind of runs in that direction, okay? And the station is just here. And if you go now, the construction obviously is finished long time ago, but they left the props in place, and you can still see them. They made it part of the architecture. Normally, props you take off after construction, but in this case, they made it part of the design. So, before they started constructing this, the companies which were in charge of design and build had to sign in contract with their names on it that the set tunnel may give Big Ben the pizza tilt. Everybody knows what Pizza Tower is, and they started publishing. This is the Evening Standard, which is kind of slightly tabloidish newspaper, but they put that next to the Big Ben and say, "Oh, it's all going to go tilty." There were Sunday Times following. They also came up with something similar. What they are trying to do. Here is the tower, and here is where the tunnel is going to go. This is a very big hole people are trying to create, and therefore this whole thing is going to tilt this way. Yeah. So, so that is actually what the plan was. That there is the Big Ben. This is to scale, and this is the Jubilee Line Extension Station, and that is 3 levels. So you got the station area at the ground level, 1 level below to cover link to one layer of tunnels, and another level below to another line. Okay, so these are big civil engineering projects. What they came up with is this tube mache technique, where you make a hole in the ground, a shallow hole, and you inject tubes across and pump grout. And the idea is, as they would observe the tower, and as soon as the tower starts to show some settlement, you will pump grout at high pressure to try and hold it in place and stiffen up this clay. And the actual tunnel goes somewhere below. So you need to inject this grout layer between the tunnel and the structure you're trying to protect. That is the plan, right? And the expected settlement was basically this level, whereas the severe settlement without any compensation grouting is this level, and this is not acceptable. And 2004, and that is the glacier, and here is what you got today. Completely the ice cover has disappeared, and you got these glacial lakes with glacial till underneath it. Same thing in Switzerland. This is a mountain. it used to be like that, and if you go today, it will be like that. And clearly, if anybody says these are not our government at the time to compensate for this. You have mining issues like open channel mining, which you can see clearly. Things like this, California mining waste being transported, and so on. So all these are engineering challenges. And if you think that civil engineers have no role to play anymore because we know how to make concrete, you're, I'm afraid, sadly mistaken. Because making concrete is not the issue. Solving problems is the issue. And problems are continuously changing. That is the main point I wanted to make. Now I move on to a little bit closer to what we will be talking in this course on resilient structures against earthquakes. This is a building that has perfect structural engineering. Senthil Sab has done a great design. No problem with the structure, right? However, the whole building is now on its side because the foundation has liquefied and the whole thing has fallen. Nobody is going to use the structure. No point how well you make the structure if it is going to be at 60-degree angle to the ground, right? So, in the end, the structural engineer will always blame the geotechnical engineer and say, you guys don't know what you're doing. And there's some truth in that. I will show you some of the pictures. These are the Haiti earthquake that I have taken a team to, and that is the presidential palace, which itself has collapsed in Haiti, Port-au-Prince. And no engineer is going to make stairs that way, right? You can't climb the stairs upside down. But that's because this was attached to the other building, and as it went, you can see it was not great. And you could, I mean, this is a structural engineering problem. Beam column joints seems to be a specialty of ours. We can't seem to put enough shear reinforcement between beam and column. And again, I'm a geotechnical engineer, but I should know enough structures to say, looking at it, yeah, it's clearly there's no shear connection between this and that. And as the thing started to shake and open up and close, you can see where the cracks are happening. This is what you call pancake collapse. You lost a floor underneath. Typically, buildings in India, you open up the ground floor, put pillars, remove even one pillar, and create showrooms. Because ground floor means showrooms for us. And it's all fine normally. When the earthquake comes, you'll get found out. And that's what happened to these buildings. I hope this place, now with the advent of, I mean, we used to go on site visits and see like that, but now you can actually, so many mobile phones are there, and you get images like this. This is a Mexico City earthquake in 2017. People are there still, they're feeling the shaking, and the building collapsed right next to them. So now we are getting to see actual failures happening in almost in real time. Now, we'll try and I'll try and steer you more towards soil liquefaction now. You got what's I'm going to try and keep it as simple as possible to start with. What is soil liquefaction, right? So As an undergraduate, we all would have done this shear box experiment. It's almost the first or second lab you would do in any. Contract, dense and dilate. How does that manifest? If I were to plot the shear stress and shear strain, the dense sand will come to some peak strength and it will strain soften to get to the critical state. The loose sand, on the other hand, will constantly increase the stiffness and it will reach the same critical state. So, this critical state is a Cambridge construct where what we say is that if you shear anything long enough or enough shear strain is applied, all soils will reach this magic state called critical state, beyond which you cannot have any more increase in your shear stress. I can keep increasing the strain, both these lines will go horizontal. This is exactly the same as what the structures people do in plasticity. Once you've reached your plastic limit, you assume that you're not going to get any more increase in your strength, only you accumulate more deformation. It's the same concept as that. You can also look at this from volume perspective. This is the volumetric strain, and as I apply the shear strain, dense sand initially does a little bit of that and goes up, whereas the loose sand continues to contract. So, the dilation is marked positive on that axis. So, this is very straightforward, and you must have done this kind of experiment before. What about saturated soils? When you have saturated soils and you're trying to shear them quickly, rapidly, then your soil wants to undergo volume change, as we just saw. But for it to undergo volume change, the water between the pores need to move out. So, if I'm reducing my overall volume, the pressure in the pore water goes up, or the water has to flow out of the thing to keep the same pressure. If I am dense and I try to shear, the volume wants to drop, which means my pore water must go into suction, right? So, loose sands, we expect increase in pore pressure, and for dense sands, you see a drop in pore pressure. Very simple. So, when you try to do this kind of rapid shearing, the rapid shearing I am choosing because it is like an earthquake type load. You are applying 1 to 5 hertz. So, you are doing this shearing at that rate. If you do that, there is no time for the pore fluid to go out. Therefore, the pore pressure will change. Because everything in soil mechanics is linked to effective stress by the Terzaghis effective stress principle, if I change U, I will change my effective stress. If I change my effective stress, I'll change my soil strength, stiffness, the whole caboodle. So, this intergranular effective stress is the bit that allows you to carry loads, and if you are messing around with that, that will change. So, just to apply this, if my pore water pressure goes up, then my effective stress will come down, right? Because if that goes up, this is the total stress that's not changing. So, if that number goes up, this comes down, and that's what you would normally call liquefaction. In fact, you can make the pore pressure U go up so much that it will match the total stress. If U equal to P, then this becomes simply sigma dash is 0. If sigma dash is 0, your soil is no longer soil, it's a soup. So you can't make buildings stand on soup, therefore they will sink, rotate and fall down, right? So that's basically what liquefaction is. If it matches fully, then it's called full liquefaction. If it's say 80% or 90% of sigma, then you would call it as partial liquefaction. Both can have its own dangers. We'll come to that later on. So how does this reflect in the change? This is, by the way, from a centrifuge test. So this is actually real data. So with time, with the earthquake, the pore pressure builds up. So at this point, my stiffness on the tau gamma plot is quite high. The slope of that loop is my shear modulus, or G, right? Tau versus gamma. dt or d gamma will be my G. So initially it's very high. So my structure is happy, sitting on the top of this stiff material. But as the pore water changes, my loop is now opened up and also rotated. My stiffness is come down. So this is some case of, say, partial liquefaction. So if I play it further, now I'm almost close to liquefaction. My loop has now fallen down. I have almost no stiffness, zero stiffness, and therefore my structure will start to sink in. And how does that feel? This is year I was born. Me and Professor Agnihotri were born, 1964 Niigata earthquake, and there was this real great Japanese engineer. This earthquake was happening at Niigata airport, and everybody were kind of running away, and this guy decided to take his 8mm film camera and shot this. And this is a real good evidence of how liquefaction actually feels in the earthquake. You can see the airplanes and how the water is gushing out, and clearly a lot of settlement because of this, and it's a real footage of liquefaction back from 1964. And as a result of that, this is a very classical picture almost everybody will show around the world, where again beautiful structural engineering of Japanese engineers. None of the blocks had a crack in it, not even a crack, but they're all on their backside, and therefore they had to be demolished. And this is the problem with liquefaction. Typically, you would see sand boils like this. Whenever you visit earthquake affected areas, we can say which bit has liquefied, because you'll always see sand boils like this. And there are many consequences of this. For example, buildings can sink and rotate, embankments can move, and so on. Haiti was another example. I showed you some pictures before, but this is now with liquefaction. This is the main port which is supposed to deliver the relief goods after the earthquake. And as you can see, no engineer would put a crane, a gantry crane, in the middle of water in the bay, would they? I mean, this is where all the ships are supposed to come. You can have one here and one there. And the reason is this whole structure that used to support it has fallen down thanks to liquefaction. And therefore, when we showed up, it looked like this is standing in the middle of water. And here you can see there was a lot of lateral spreading. If liquefaction happens on sloping ground, it will spread. We'll come and do that properly later on in the course. But if it spreads, you can see these longitudinal cracks that are developing there. And one of those is this, and I'm standing in it. I'm not a short fellow, so it's come up to here. So the cracks are about that deep. And you can see the ground picture of that crane as well there. In our own, these are from different earthquakes. This is a shallow foundation failure in Christchurch. If you look from outside, the building looks okay. It's only a one-storied building, but you can see careful. If you compare the building to this, you can see there's a tilt. So all that has happened is the whole building has rotated, sunk a little bit and rotated. So if you are vacuuming the floor, you're always trying to go up the floor. In the end, they demolished those houses. This is the Kandla Port Harbour Masters Tower. It was supported on pile foundations, and the pile basically had punch on one side, and the whole building has rotated by about 7 or 8 degrees. It's quite visible. These are river embankments next to River Avon in New Zealand, in Christchurch, and you can see all these same kind of cracks we have seen before. With lateral spreading, you get these kind of longitudinal cracks. This is from Musini earthquake in Ecuador. One of my students went there, and that is from Bhuj earthquake, picture courtesy of IIT Kanpur. Now, if you put pile foundations, first time I'm mentioning pile foundations, so into these kind of moving ground, sloping ground, which is going for a walk, the piles don't like it because they are standing vertical and the whole ground is gone from this side to that side. You can see the whole thing has rotated. Now, I got a frame on the top which is trying to hold these piles straight, and the piles are trying to be pushed that way. This one doesn't want to do the same. So, at the top of the pile, I'll get a hinge. Even concrete piles can form plastic hinges. As you can see, they form that by forming these kind of spalling of concrete and so on. So, I had one hinge here and one hinge here. Same thing happened in Ecuador as well. These are not big structures, but the mechanism is very clear. So, based on this, we came up with this kind of two-pin mechanism where you can have spreading like that and you form these hinges. Again, I will come back to this and do this properly later in the course. One of the most, it's not very old, this earthquake happened in Sulawesi in Indonesia, and this was another big issue with liquefaction. After the earthquake, this region was looking like this. Okay, you got lots of collapsed buildings. By now, we got used to seeing collapsed buildings. But what we are not used to seeing is roads getting crumpled up like this. And maybe in parts of Andhra, the roads are already like this, even without the earthquake. But that's just for us to worry about. But these roads were fine the day before, and they turned up like this, and buildings got collapsed on the both sides. And you won't see what caused this until you go to air. Once you start looking at aerial pictures, you start seeing this kind of damage. And this is the one I want you to take. This is stitched up satellite images by a company, and I'll play this for you. And you can see what happens. Oops, what? Are you not playing? So, those are actually stitched up based on satellite images, and forgive the dramatic music. But before and after is quite clear to see. This is how it was looking before, that's how it looks after the earthquake. This is all because the ground liquefied and started going to walk like a river, as you have seen. So, nothing makes the point better than a good visual. And similar kind of things with pile foundations we saw in Christchurch, where the moving ground, basically whether it was steel piles, concrete piles, solid square piles, all of them were forming hinges on the top, and you can see the whole thing got rotated that way because this ground was going into the river. And I can show you many examples. In fact, there are publications in geotechnique. If you are interested, you can look at the new mechanism we were proposing based on that. Another thing that can happen is if you have tanks below ground and the soil liquefies, these tanks want to, if they're below ground, the weight of the soil is keeping them down, right? If the ground all turns into liquid, even temporarily, these want to float up, especially empty water tanks, oil tanks, and so on. And many times they do. Here is a a tank that tried to pop out because all this ground liquefied. And similarly, in the Ecuador earthquake as well, we had similar examples. And if you have pipelines, they tend to float up. Along the length of the pipe, you can see it has gone up and then fallen down. That's why you are seeing this. And where you have manhole covers, in Japan particularly, they tend to pop out a good meter or so, because the whole pipeline has come up by that during flotation. So pressure. Don't worry too much about the maths and the equations, but that's what we are trying to do. We are going to solve the solid bit, fluid bit, overlap them together. And at every time instant, because it's a time domain thing, you need to iterate between the solid phase and the fluid phase until there's convergence, and then you time march into the next time step. But that's all maths and computational mechanics, if you like. What's most important is, to be able to do that, we need advanced constitutive models. We need to tell the computer what the soil is going to do if you apply a certain stress and strain. That is what you would call a constitutive model. If you don't know what the soil is going to do, the computer ain't going to tell you what the soil will do, because you need to give the rule, right? Otherwise, there's no this thing. And also for liquefaction problems, particularly, it's you're setting the computer to fail, because you're asking it to solve a problem where the system is going to near zero effective stress. If the effective stress is near zero, the stiffness is going to be very close to zero. And if the stiffness is zero, how is the computer supposed to find convergence? It will run into numerical trouble. And a lot of times this happens. And there are ways around it. I think Professor Agnihotri will talk more about it in dealing how Praxis deals with it. But liquefaction problems are really hard problems to do this particular thing. And also on top of that, you have to have boundaries, and you must have either a non-reflecting boundary or absorbing boundary as well. But the constitutive model is the big thing for us. We had a code called Swandine, which I used for many years, and we were for fun playing games with this. And here is the Kobe earthquake created this kind of gravity wall movement. It moved and settled. Somebody just did a centrifuge test on that, and I did the numerical analysis. My colleagues analysis of this. And one of the funny things is that when you shake the tunnel, it doesn't pop out because the soil liquefies. Here is the input acceleration and here is the increase in pore pressure. But the displacement, if you plot x versus y, so the tunnel or the pipeline does that. So it's shaking horizontally while moving up. And that's why you are seeing these oscillations while it started there, it ended up here, some movement of nearly half a meter, but it is not going in one step. It is going in stages. So to do this kind of thing, we had to go with a rectangular tunnel. This paper is, by the way, published in Indian Geotechnical Journal, and me and my son during his holidays ran this analysis, and it came out good. So we thought we should write a paper on this. And okay, we gave it a sinusoidal motion and saw what's happening to the accelerations. Those are all reducing, pore pressures increase, and the tunnel moves there. I should have an animation of this. So if I were to, so the bottom is where you are seeing where the current time is, and the pore water pressure is on the color, and the tunnel location is shown. Oops, why do you do that? So as you go through this, as the earthquake hits, the pore pressure is built up and it's going, it's almost fully liquefied, RU of 1, and you can see the tunnel move up. As it tries to move up, the question was, of course it's going to move up. It's lighter than the soil. Why would it not move? It will move. But what stops it? You know, why is it not floating all the way to the surface? Surcharge is effective stress is 0, right? So there's nothing to stop it. As it tries to move up, you can see in the pore water, it has to create some suction. It's that suction that is holding it down. And this was just numerical, right? I mean, my son just graduated, so I didn't believe him and he didn't believe me. We thought this is what we will say. If you read the paper, that's what it says. We have no experimental evidence, but this is what computer analysis is showing. Now I have a PhD student who's actually done centrifuge tests and showed this is what happens. But this came 2 years ago. This paper was published back in 2014. So that finite element analysis is one way of doing it. Another method it's come more recently is this MPM method, material point methods simulations. There's a code called Anura 3D. And this is good for some large displacement problems. For example, if I have a slope like this and let it fail, it will go like that. This kind of works on the change of momentum equations. This is why it kind of does initially some bad things, which are not physical. But the runout distance and the slope, final slope seem to work okay. This is very much a new method. People don't know too much about it. So people are trying and for different problems. This is done by a colleague of mine. And now he's a professor at Texas A&M. They also try for, this is a very important problem of subsea slope failures. And there are some classical examples around Norway and Japan, where the subsea slope failures cause the soil to run for kilometers. Once they start going, they don't stop. So this is a bit like our lateral spreading, but the spreading happens over the lengths of kilometers. You can see that is nearly 2 kilometers, right? And the width is about 2 kilometers also. Let's see what the analysis predicts. This is the underwater survey revealed. This is the historic slope failure, and they created an analysis of this, and you can see depending on the topography, that's what the computer is predicting. Clearly under predicting, but it's not too bad for something you're trying to do. Okay, I'll try and do this quickly, but tomorrow or some time I will come back and we will go through the principles of this. It's actually not that hard, but imagine I can have a small scale model of a real problem. So if I have imagine a dam of 100 meters high, in the lab, I can't build a 100-meter high dam, but I can certainly build a meter high dam. So I build 1 meter high dam in the lab and put it on the centrifuge and spin it at 100 times Earth's gravity. So the soil underneath the dam will think that it is actually below the big dam. So that is basically what centrifuge modeling is. You scale down the model, increase the gravity by the same factor. Our centrifuge is this, which is about 10 meters in diameter, and it can carry 1 ton of soil up to 150 times the Earth's gravity. And I'm going to skip this because I'll come and do this properly later. What I wanted to show you is how does actually gravity feel. The theory we will cover, he will black out for sure, right? And that's where what happens to human being at about under 10 G, it's about 8 G. We are putting our soil in the same kind of machine and taking it up to 150 times Earth's gravity. So it's not a nice place to be. Certainly, I don't want to be in it. Soil has no option. We can do the same thing while the thing is spinning around. We can also shake, and this is what my specialization is. And there are some issues. We want to mimic the earthquakes in a centrifuge, but because of the scaling laws, which I'll explain tomorrow, we need to apply big forces in very short time, which means I need quite a lot of power in my actuator. And we must also be able to simulate earthquakes. So the first one I built was this SAM actuator, and this is cheap and cheerful. The whole thing costed less than 20,000 pounds to build, and we made it in-house. And it can go on the centrifuge. You can put a package on it. All it is a motor and a flywheels. I store the energy into the flywheels, and there's a fast-acting clutch which will grab onto the reciprocating rod and shake this. That's all it is. Very simple thing to do. And this was very successful. We worked for 10, 15 years and produced maybe 12, 13 PhDs for me. So it's done quite well. And it will usually produce earthquakes like this. It can only do sinusoidal motion or swept sine wave motion and very clean earthquake at one frequency. That's what it could do. Then we thought we want to upgrade to the servo hydraulic shaker. So we started designing and building this ourselves. Actuator we had to buy and from team, and the rest of it we built ourselves. And this one has specifications of like it can work out 80 times Earth's gravity, it can apply earthquake of 0.5 G, carry about 200 kilos of payload, and the most important thing is it can simulate realistic earthquake motions, not just sine waves. And it can accept all our existing containers as well. So that was our shaker. And then we put it on the centrifuge and place the table, the model container with just level bed. It's a trail experiment we were doing. And then we all get very nervous because those cylinders hold oil at about 300 bar pressure. And once the centrifuge starts rotating, they're traveling at about 200 miles an hour. So there's a lot of pressure, not just in the cylinders, but in also us. You can see it in our faces. And then you kind of hope for the best and press the button, and it does the earthquake. And here are some examples. That's the Kobe earthquake it could simulate. This is the Imperial Valley earthquake, El Centro motion, and so on. But now we can actually, most of our customers come and say, we want, especially Italians, come with their own Italian earthquake, Tolizzo earthquake or something, and say, can you fire that? I say, okay, we load the motion and it will do the motion we give it. I will talk about applications on piles tomorrow, but here is something fun I'd like to do, which is, this is commissioned by BBC. By the way, this program is available on YouTube. You can all go, and if you type in ancient apocalypses, Sodom and Gomorrah's events, you will see the whole episode. Basically, what there was a geologist from Canada who said that these two cities, which are mentioned in the Old Testament, disappeared because of an earthquake. And it wasn't hand of God or anything like that. because the Bible says those two people of those two cities were sinful and therefore they got punished by the God. And this guy said, no, no, it was a big earthquake that can happen in that part in the Dead Sea. There, it caused liquefaction and these whole cities disappeared. And these were all 4,500 years ago. So they sent a geologist to get the layering of that place right. They came to us and they said, this is the layering, can you do some experiments? And I said, sure, uh, we can do that. And this is what the model they wanted. So before the earthquake, you got rows of houses on a slope, and the slope had this silt layer on the top. So the soil here is liquefiable, but also this silt stops the excess pore pressure from disappearing. And we thought what will happen is it will flow something like this, and the water will come and submerge that. And we did that.
Of Sodom and Gomorrah.
So this is the clip
The
from
idea is to see whether if there is a medium strength earthquake, is it possible for these villages to actually have disappeared?
G. The model has 50 times the force of gravity pressing down on it. The houses will now react like life-size buildings. This is the point when the earthquake can be fired.
Salmon.
I think that's yeah, that's the, you can see the whole program later on, but basically that's how a centrifuge test works. And what we get is data from it like this, where we can measure the accelerations on the soil and also on the buildings, and what the pore pressures have done during the earthquake. And you can see the liquefaction of, you saw that rock flour that was deposited earlier that came and formed these sand boils on the surface. As I said, they always indicate liquefaction when that happens, even without the instruments. And okay, we got the pre and post pictures of the model village and so on. And we give this back to BBC. One of the things they're very good at is to create this kind of visualization based on what was given to them. So they thought this is how. Okay, so that's a good example of what happens to what lateral spreading can cause, and how some of the fun things you can do even going historically. Now, last bit I wanted to say is protecting against the sea levels. This is the kind of seawall defenses people are now constructing. This is in California, and that is a person to scale, and you can see how big these are. They're good 20-25 meters high. And the idea is you can put these K-zones and reclaim the soil behind, put reclaimed soil behind it and have a sand foundation, and hopefully they'll all work. But a better way of that takes a lot of concrete. So this Japanese company called Geeken have come up with this dual wall concept, where you have two walls that are tied at the top. And I'm going to go quickly. So you all heard of the Sendai earthquake and how the existing tsunami walls got overtopped there, and it created boats ending up on top of houses and all kinds of things. Obviously don't want the boats to be on the top of buildings, right? So that has happened as a consequence of the tsunami. And so this company, what they want to do is to put sheet pile walls on next to one another and tie them on the top. In fact, they're doing this in a place called Kochi in Japan, all along the coastline. But again, you want to see how well they work. So you could do this numerically. There are also experimental data that has happened. And you can see that when you shake this, the soil on either side of the wall liquefied, but the soil inside hasn't liquefied. In fact, it's going into tension. Why? Because these walls are tied at the top, which means when the soil liquefies, the walls want to splay, right? If it wants to splay, the soil inside says, no, you can't. I'm here. I'm going to go into suction. And that is what holds it together. Exactly the same way as the tunnel, if it wants to float, the suction underneath is the one which is stopping it. So the link between how soil behaves and how pore water pressure is generated is critical in problems like this. That in fact tells you whether the thing is going to work or not. Okay, I'm going to stop there. I hope, although we haven't touched so much on pile foundations, at least you got an idea of why we do research in this area. It's very interesting to start with. You saw we are dealing with problems of current construction, past construction, modeling historical events, all kinds of fun stuff you can do. And that's only possible because we have the time and good students to sit down and think about things. Equipment, finite element codes, all these are secondary in my opinion. What we need is some thought that goes into the place before you start your PhDs or masters or whatever. And if you do that, then you'll enjoy it a lot more. And if you enjoy it, then the results will follow. If you start the other way around saying, if I do this, what job will I get? The answer will always be, no matter what you do, you'll get software job. Then you don't have any interest to do what you're doing now, because I'm going to end up with the same thing. Typing C code or C++ code until AI starts writing faster than you can, then you're out of a job. So don't go that route. Enjoy the problem you're trying to do, and what is the best you can do for that particular problem. And then you need not be told. Your supervisor or a guide did not tell you to do work. You will do it yourself because the problem drives you, because you want to find a solution. We are humans. We are inquisitive. Okay, that's about it. A lot of acknowledgements, obviously, for putting a presentation like this. A lot of PhD students have worked with me. A lot of funders funded me. A lot of my colleagues helped us over the years, and so on. Okay, I'm going to stop there. The next lecture I have is on more static, and we'll now start going into pile foundations. So, what shall we do, sir? Shall we have a 5-minute break, or what time is lunch?